Welcome, everyone. Welcome. Welcome. Today is my pleasure to introduce our speaker for Wednesday's seminar, Nick Jewell. Nick Jewell, like me, is a escapee from a math department, and he is doing work on a lot of interesting statistical and health-related topics. He is in the School of Statistics and Math and Public Health at UC Berkeley. And today he will be telling us about a statistician's challenges with HIV and AIDS. Thank you very much.
Thank you. Thank you very much. Thank you for the Institute for the invitation to come back to Seattle. It's always a pleasure to be here. I have many friends in the School of Public Health here, so it's always a pleasure. I did actually offer a few talks, and so this is the one that you got stuck with. So it's a little bit of a shameless story of what I did since I arrived at Berkeley from Princeton, which happened in 1981. And most of you are younger than I, so may not know that what was happening in San Francisco in 1981 was that actually happened to be the peak of the HIV epidemic in San Francisco. We didn't call it that then. We didn't know what it was exactly. And I happened to arrive as an assistant professor and got involved in what, of course, turned out to be a tragic epidemic for San Francisco, and is still a tragic epidemic in many places throughout the world. And you'll see that a little bit evolve as I tell the story. So this is a very, as I said, a shamelessly personal view of some of the statistical issues. I have probably more slides in here than I'll talk about, so don't worry if I start flashing through them quickly. Feel free to interrupt and take me off in a different direction. It's your seminar, not mine, so you can use me whatever way you want. I will try and keep things under control if you get too rowdy, as Abby said. So I'm going to just sort of illustrate a little bit. So I want you to sort of put yourself in a position of a statistician arriving or at the beginning of an epidemic. And there's been several, obviously these things happen over time from time to time. There's been nothing quite like HIV/AIDS in my lifetime, but there undoubtedly will be something else. And it's sometimes hard, we get so used to knowing so much now about HIV/AIDS, I want to try and put you back into a position when we knew nothing. As I say, we didn't even know it was an infectious agent in 1981. So I'm now going to try and work this thing there. Okay. All right. So one of the things we didn't know about was first of all, whether it was an infectious agent. Once we figured that out, or when I say we, I'm using that in the very British royal way of taking credit. Of course, I had nothing to do with it. Once it was figured out that it was an infectious agent, there was a tremendous amount of interest in the natural history of the disease, in particular the incubation distribution. I'm sure all of you know that. And I should have said up front that I'm a little nervous about giving this talk because there's probably on any given slide, someone in this room who knows infinitely more than I do about this specific slide. So I apologize and feel free to correct me if I make a mistake. Remember, I'm just a statistician, not a clinician, not a virologist. I know very little, just a little bit of statistics. The incubation period is, as pointed out here on the slide, it's loosely defined as the interval of time between the date of exposure or date of infection, really, and the date of diagnosis, in this case with AIDS. And that was intensely interesting in 1981. We knew of a few cases. As I left New York in 1981, the New York Times had run the Sunday Times Magazine article about the gay cancer. There were a handful of cases in New York City amongst IV drug users of either pneumocystis pneumonia or Kaposi's sarcoma. These were unusual, and the New York Times started running stories, but we were talking about small numbers. Did not seem to be concerning. Again, back in 1981, if you were gay and a male, you had just lived through the 1970s. In the 1970s were the transmission and explosion of hepatitis B through the gay community also, and the beginning of the trials for the hepatitis B vaccine. So the gay community was understandably concerned about what now. And this, in fact, was the first paper coming out of CDC. And by the way, when I make these comments, remember these are historical. These guys were writing this when we knew nothing. So please don't take this as any criticism. This was a paper that came out from many of the people that had a significant impact in understanding HIV at CDC at the time. And this was the first paper out on estimating the incubation period. How quickly, what happens to you when you get HIV infected? How quickly do you get sick? And of course, hidden in there was what fraction of people get sick. I think when I arrived at Berkeley, most people, the dogma was that about 10% of people who got exposed to this virus got sick, and you would get sick in about a couple of years, and the rest of you were fine. Of course, as you know, that was radically incorrect, but here was the first attempt to do this. It was quickly determined or quickly realized by statisticians that you have a problem in estimating incubation when you don't know that who's infected and you don't know when it starts, because most HIV infections are asymptomatic. And you can see in this paper, if you can read the text, that this was realized immediately, that the incubations that people actually saw because they'd seen someone get sick represented a length bias sample. They were seeing the short ones because they'd already happened. And you can see that stated eloquently here, that they're short compared with the average, and the cases with long incubations have not yet been diagnosed and not yet been observed. So they knew this. And so they had in their hands, these were actually transfusion cases. Transfusion cases were useful, and I have to be careful with the words here, tragic for the individuals, but useful from an epidemiologic point of view because we knew the date of infection for a transfusion case. And we knew the date of diagnosis. So you actually knew the incubation period for these patients. Almost all of them white males, which will tell you who was getting blood transfusions in the United States in the early part of the 1980s. And if you just took the simple average of those known cases, you got a 2.6 years incubation period for HIV. And they knew this would be an underestimate, and then they corrected this, and how they did this was by using statistics and by using models for the incubation and showing that the 2.6 was completely wrong. See if I can, yeah. And here's actually from the same paper their estimate of the incubation period associated with HIV. And you can see they came up with an estimated mean almost double that 2.6, which was in the observed data, to being 4.5 years. And so they realized we're underestimating the length of time that we're going to see. Now, of course, we're sitting in the next century. We know this is off by a factor of at least 2 also. So beware what statisticians say at any point in time about something we know nothing about. It's better than 2.5, but it was actually well off the truth, even if you're talking about incubation in days prior to effective antiretroviral therapy. So why was this off so badly? This was off badly because even though the statisticians understood the nature of truncation, and if I can get away with this, I'm going to use the board just a little bit. So if you imagine the distribution of the incubation period was something like this, I won't put a scale on here, but what they were seeing here was, of course, some little piece of the, one small piece of the truncation. Imagine that you would only be seeing data in here. So what you're doing is you're just seeing this piece, a conditional piece of the distribution. You then fit that, acknowledging the truncation, and you fit a shape, and then you use the model on which you said, this is our estimate of the distribution, to extrapolate out to the rest here. That's pretty good if you're truncating up here. because you'll get a sense of the right distribution here, because you're seeing most of it. And you'll be able to extrapolate, even if you get it not terrifically out here, it won't affect that much because it's only a tiny piece. The trouble is we were here. We didn't know that because we didn't know what the incubation distribution was. We didn't know how long it would take. Yes?
The abstract you just showed had an upper bound of the 90% confidence interval of 14 years. It doesn't seem to fit with this graph.
Oops. It did have a 90% confidence interval from 2.6 to 14.2 years. That in itself, the question was, how does that jive with the graph I just put? Remember, this is the confidence interval for the mean. It does give you a hint that there's a lot of extrapolation going on here, even with the assumption that the model is correct. So that hints at what I'm saying. It's not the confidence interval. This is the whole distribution here. That confidence interval is just about what's the mean.
Yeah, but it tells me that they have a different shape of the curve.
No, this is actually the parametric model-shaped curve. But as I said, the spread of this certainly influences how accurately you can estimate the mean. But that's not the only thing that will influence the width of that confidence interval. It depends where you're getting data. They did not see data over this entire range because you've got 10 years here. There was no data up here at all. This is all extrapolation. The point is that the extrapolation was based on a model, and that's why things got wrong. I'm going to point out here that the parametric models are terrific, but not if you're here at the very beginning of an epidemic where you only have a little part of the early part of the curve. And later, non-parametric estimates showed this more explicitly with even wider confidence bands because the non-parametric estimates can't extrapolate and they reflect, I think, a little bit more of the true uncertainty. And so quickly, as cohort studies were developed, the non-parametric estimates showed, even on the transfusion cases, the non-parametric estimates showed we don't know yet what the incubation is. And then as time moved on in the 1980s and cohorts were assembled, we started to get a picture. The non-parametric estimates displayed the enormous amount of uncertainty that was actually present in the transfusion cases, that they really weren't enough to pin that down. And
when you say non-parametric, they were modeling the density as with a smoothing spline or something like that?
they were just making no assumptions about the shape of the distribution. It could be anything. So no assumptions whatsoever. That's what I mean by non-parametric. Of course, that means you can't extrapolate. So that in itself, you can only estimate the piece you see. And non-parametrically, it was clear that if you tried to extrapolate, what you could identify from the observed data could lead to a vast range of different possible incubation distributions. And I'll come back to that in a second about the implication of that for other purposes. I got involved in this a little bit because no one had really figured out quite how to understand the properties of non-parametric estimates. And this was a paper that a student of mine at Berkeley, who's now at Johns Hopkins, Mei-Cheng Wang, wrote, understanding, and I don't want you to read this because this is theoretical statistics, but understanding the properties of these estimates when you don't make a model assumption. Just as a quick aside, I mean, this is a little tour through history. Later on, people really started to try and use additional information to pin down incubation in addition to just the time from infection to the onset of symptoms. Because in cohorts, there were a lot of individuals who provided incomplete information. They hadn't yet developed AIDS, but we knew how sick they were. We knew biomarkers for the disease, their viral load, their CD4 count that allowed, and people became interested then statistically in using what are known as marker variables to try and improve the estimate of the time of infection, because many cohorts were assembled with people who were seroprevalent and we didn't know when they were infected. But you could see their biomarkers at recruitment and make a reasonable statistical guess at when they were infected. And simultaneously at the other end, if people had not yet developed AIDS, when you're following up a cohort, we could use biomarkers to project when they might and get better estimates of the incubation distribution. And this led to a whole sort of idea around these marker processes in survival analysis to try and take account of this information. And you can see this in the paper here, to use markers as surrogate response for failure with sensor data. That means when, in the lingo here, or in the context here, biomarker as a surrogate for when you might get AIDS, even though you haven't yet. So we can get better information about the incubation, and simultaneously using markers as predictors of the time elapsed since onset of a survival process, in this case onset of infection. Okay, so why was incubation important? Well, it was important to understand the natural history of the disease, to understand for clinicians what was happening. It was also crucial to try and understand how big the iceberg was that we were observing. We were seeing a handful of cases, now 20, now 100, different risk groups and so on and so forth. But how big, we knew at this point, people are getting sick at varying points of time. There's a big iceberg underwater here that we can't see, but we know it's coming. And how quickly it will come and how big it will be will depend on what the incubation distribution is. And that led to this idea from Ron Brookmeyer and Mitch Gale as a method of counting how many people there were, in this case in the United States, who were HIV positive. That was a crucial piece of information. How big a problem do we have? What resources do we need? How can we measure if we're making any impact if we don't even know how many people are actually going to get sick? And here's the basis. I don't know how much I think this is a fairly mathematically sophisticated audience, but here's the basic, very simple idea or equation underlying back calculation, which is that if A here is the cumulative number, the Scottish people, by the way, have an unusual spelling, just to alert you to that. We don't, we speak English a little bit differently. The number of AIDS cases by time t, let's say from the beginning of the epidemic, so that's A, that's the thing we'd like, that's the thing we might start to see, because we see AIDS cases. It depends, of course, on how many people are getting affected over time, and then how long it takes from the moment they get infected till they show up in our counting system, because we're only counting AIDS. AIDS was reportable. HIV infection has never been reportable per se, at least in those early years. Now it is, I don't want to get into that story, but we didn't know, of course, there was no way of knowing it, who was the number of HIV positives. So this is just a simple integral equation. What do we know about this? Well, we know A. That's what we see. That's the data. You could get these number of AIDS cases in the United States, in California, amongst risk groups, however you wanted to break it down from the CDC. We now thought we maybe know about the incubation from transfusion cases from these cohorts. That's why incubation is important. And now we just want to deconvolve this equation and estimate G. That was the idea behind back calculation. It was very useful early on in the data. It was fairly imprecise because of two things. One, we were seeing early counts of this before many people, and we had a lot of uncertainty about the incubation distribution, which is really the Achilles heel of the back calculation technique. And back calculation quickly became, so it looks so simple. It has all the problems, by the way, of what we call in mathematics inverse problems, that deconvolving something like that, if you go back to this equation and you think about this and try and explain it to someone who doesn't understand mathematics, here, you've got this signal in here and it gets smoothed out by incubation. You have these people arriving with infections, and then you smooth out when they will show up in your system by this incubation distribution. It's crucial that F is smooth, that incubation isn't weird. And then this is what you see, the smoothed out signal, and you have to say, this is what I see, what signal produced this A, given I know this filter. And that's a tough problem mathematically. It's made much tougher in the real world because of lots of things started to cause problems with the data. I mean, practical stuff. Stuff that statisticians have to worry about and that you guys have to worry about, I suspect, all the time. Down here you can see this reporting delay was suddenly a huge problem because remember early on we needed every case we could get, but cases were getting reporting delays of up to 6 months was not unusual. And so what do you do with the data that's 3 months old? You know they're there, but they're not the full count that will show up 6 months for being diagnosed in a certain month. It took time for cases to make it their way through the system. It was not instantaneous when someone is diagnosed that they show up in the counting system.
You should put that in your F.
Yeah, you have to put it in the F. Yep. And that's another distribution you have to estimate. You have to know about, well, what is the reporting delay distribution? How do I figure that out? That's another truncation problem, by the way. We started to see the fact that there were seasonal effects on the diagnosis rates. So people don't get diagnosed just when they get sick. People get sick and go to doctors. That's affected by a whole bunch of things. It's not just, I get sick, oh, I go in, I get diagnosed instantly. I put it off. If I get sick now, I think, Thanksgiving, I don't feel great, but I got to get through Thanksgiving and then I'll go. I've got to get through the holidays. So you can see actually a marked increase in AIDS diagnosis in January compared to December. That's just human behavior, but it fouls up the use of back calculation, and you have to worry about that. And of course, what really happened, just as the data was starting to accumulate, tragically, but data was starting to get us a handle on it. We were seeing enough A's that we could maybe figure out what the G was. The incubation started changing on us. It was non-stationary. It started to be lengthened because people started to get treated in various ways. AZT came out, and that delayed the onset of AIDS. Is of course not a simple thing. It's not a hard line in a sense, in terms of a definition. Then they went and changed the definition of AIDS from what it had been at the beginning. So lots of work for statisticians, and it turned out, in fact, that back calculation was really useful, I think, to get a sense of the scale of the iceberg, but not very good to get a precise. So it got the scale of the magnitude, but not anything better than that. And those subtle changes in incubation, subtle changes in that filter made a big difference in estimates of the incidence curve. Enough that we knew in 1986, 87, that the epidemic in San Francisco had ended in 1981, ended in saying a very sharp drop in the peak, before we even knew what HIV was, before there were any interventions whatsoever, before any public health professional had set foot with a policy to stop the spread of HIV, the epidemic had already started to decline and end. And that's another story, a very powerful story about the community of gay men in San Francisco and how they reacted far faster than any government or scientific officials. Okay. So now I just want to move on. Oh, this is just to finish the story of incubation. Now people don't use back calculation to estimate HIV incidence. There's still intense interest in HIV incidence, not so much in San Francisco because it's at a much, much lower level, but certainly in many sub-Saharan African countries, we still want to know about incidence. It's still at sizable rates. It's still a major issue. And now people, they don't use back calculation for that. They're going in there using cross-sectional serial surveys usually, and usually using kind of a clever idea, diluted assays, doing more than one test at the same time, because people are most interested in incidence rather than prevalence, and interested in recent incidence. And the way that people figured out, oh, we can tell, we don't know when you got infected, but we can tell if you were recently infected was by using an understanding of the biochemistry of the assays and saying, yeah, we'll give you the hard and fast ELISA test that really does detect as early as possible that you've got any virus in there whatsoever. But then at the same time, we'll take our very good test and we'll make it worse. We'll dilute it so that it will not pick up an infection. You think, why would you do that? Because if you do both tests on the same individual, they'll only be recent if they show up as positive on the very accurate ELISA, but not positive on the diluted test. And if you get an individual who shows up positive to both, you know they've been infected for some time. And that's basically the current strategy that many places use to try and estimate current incidence of HIV. So I want to move on now to another thing that was also led to a lot of development of statistical ideas. And that was to another part of the natural history of the HIV disease, was trying to understand how easy is it to transmit. And of course there were the articles in the New York Times. You know, so-and-so had sex with one person once in their life and got infected. Oh my gosh, and panic, right? And rightly so. Was it that easy to transmit? Was it hard? How many unprotected sexual contacts did you need to have a risk? How should you intervene on infectivity? You needed to understand this, and the early data on that also came from blood transfusion cases and came from the spouses or partners of blood transfusion cases. So once an individual was determined to have AIDS from a transfusion case, almost immediately you got the partner in and tested that partner immediately. It was crucial, of course, to know if the partner was themselves positive, and if not, to take precautionary steps to protect that individual. So retrospectively, you got this information, and through surveying, you would try and assess. So here's where we are in time when the partner studies were assembled. We measured the status of the partner. This is the index case. We knew when that had happened because that was the date of their blood transfusion. And then one tried to assess how many sexual contacts had happened in between. And from that, we would try and guess what's the risk per contact. What's the infectivity of the virus? And that's a little schematic, basically, of the data that you get from partner study data. And this became a very special case of what's known as current status data, which basically is, if you think of time, in this case time is not time but number of contacts, number of exposures, because we're in an infectious disease setting. But as time or exposure goes along, at some point infection happens, and the partner moves from state 0, uninfected, to state 1. You don't see this process because that would involve being in the bedroom on every sexual contact and testing them every time. That would be great for a statistician because you know exactly when it happened, but you don't get to do that. But what you do is you come in cross-sectionally at some point. This was when information was known, and you measure the partner. Are you already infected, as in this case? Or if you'd intervened here, you might have seen the partner uninfected, and from that you have to estimate the infectivity parameter from that very incomplete data. And it's actually quite easy. I won't bore you with the mathematical details. If you make heroic assumptions, it's very easy. So, and you would see these kind of numbers in the New York Times or the Washington Post. I don't want to pick on the New York Times. You know how the risk per contact numbers were floated out there. And so if there is a fixed risk per contact R, then after K contacts, you won't be infected with probability 1 minus R raised to the K. Because if they're all independent, and that seems reasonable. Each contact carries its own independent risk, like Russian roulette a little bit. So the probability of being infected is just 1 minus that. And that's fairly simple, and it's very simple and useful, as you'll see in a minute, if you transform this by what statisticians knew as the complementary log-log transformation, because if you take that transformation, it separates out the role of the infectivity parameter and the role of the number of contacts. Both will influence your risk. How much contact, how much is the risk. But it separates them out in a simple way that allows standard software to estimate this parameter here. Once you know K and you know whether the partner is infected or not at the moment you screen them. I'm not going to go through the math here. It's there if somebody uses these slides and wants it later. But now going back to the beginning of the talk, you can do this non-parametrically. I should have said this is, of course, for people who know about this, this is corresponding to what's known as a discrete exponential. The risk is constant for contacts. It doesn't go up if you have more contacts or down. It just stays constant. Each exposure has the same risk. You can say, well, maybe is that true or not? Maybe different contacts carry different risks. And certainly with some infectious disease settings, you might think that. And you can do a non-parametric analysis. That's just following this here. I'm not going to go through the details, but you can get a non-parametric estimate. And actually, there's very nice algorithms from the engineering literature that we knew about that allowed this to be estimated straightforwardly. This is a very bizarre object for statisticians. It does not have the same properties of estimates that we're used to in normality and Gaussian stuff. So this had generated an enormous amount of research into what is this darn thing. And here's the data that I actually first did. This one was called the California Partner Study. This was assembled by Nancy Padian. I'll mention her name again. She was a graduate student at Berkeley at the time. This was part of her thesis. And she had gone out and collected female partners of males who had been infected through homosexual contact or through drug use. And she found the women who were partners, sexual partners of these men, and tested them. And this is the data just in group form here. You can see whether the woman was seropositive at screening or seronegative and how many contacts had happened, unprotected contacts had happened in the interval since the infection of the original index case. And I'm going to assume here that in that schematic that I had up a moment ago, oops, going the wrong way. Here, this assumes that you know the time of the infection of the index case. Certainly easy for blood transfusion cases, not so easy for bisexual men or IV drug users. So there's another whole area of statistics saying, what if you don't even know that? But I won't get into that additional detail. So let's go back to the data. There's the answer just from that data from what I just described. It's not very hard. The smooth curve here is the discrete exponential. That's a constant risk per contact. And I've just plotted the number of contacts here on the log scale. And the jumpy thing in there is the non-parametric estimate. It's quite jumpy and spiky because there isn't a huge amount of data available. There are 159 pairs, 159 partnerships. But you can see, even with this, and you can certainly assess statistically, this discrete exponential does not fit very well. There's far too many early transmissions. The risk is much bigger early on than the discrete exponential allows for. If you go back and look at the data, there are people in here there have been a long passage of time, so there were a lot of contacts. And yet the risk at that level, when you try to project it and make it constant over the whole range, doesn't get it right. And so we knew early on this is not a very good model. You can't say there's a risk of 1 per 1,000 contacts, 1 in 1,000 or 1 in 2,000. It's just hiding what's going on. And you might ask yourself, well, what the heck is going on? Why are some contacts, quote, more infectious than others? By the way, here's the value of that complementary log-log transformation, in that here's the plotted on that log. This should be linear with the slope 1, as I just showed. If it's discrete exponential, it doesn't go through the data. And here's a less restrictive model, which goes through the data much better, and you can see it doesn't fit very well. Let me just, before I go into that, let me just say that very quickly, and I told you I'm just skating over history here. The reason why it doesn't, one of the reasons why it doesn't fit well is, or two reasons why it doesn't fit well. One is, it's not that every contact doesn't carry the same risk. It's that every partner doesn't carry the same risk. And I subtly slipped that in there. When I said R, I assumed that was the same for every partnership. But it was clear from this data early on that there are what are now being referred to as super spreaders, people who are much more infectious than others, maybe because the exposure is coming early on in their infection when they have a high viral load. Maybe the contacts are coming late on when they have high viral load. And infectivity is not constant from partnership to partnership. And from a statistical point of view, another explanation for this problem, why you don't see this model work, is it's very difficult to estimate the number of contacts accurately. And random error in the number of contacts does exactly this thing. So this lack of fit could be explained solely by saying we have random error in the number of contacts. Okay, I'm going to forget the regression. I just want to jump to this. Yes?
So how about the time after, because the infectivity is not constant by time, the viral load is...
Yeah, there's work done on that trying to estimate how the infectivity within a partnership might vary over the incubation of the index case. And yeah, but that's more complicated than this, but it's there. Just a quick point here, that you can extend these ideas to regression where you might be interested in aspects of the exposure. Did the woman bleed during intercourse? Did that increase her risk of HIV infection? The answer is yes, it did. Anal intercourse being part of the normal, part of the contact, etc. And this one here is whether they use condoms regularly or not, and I'll just go straight to the curve here. Here's the curves fitting the basic model. Here's the curve amongst no condom users, and here's the curve amongst condom users. And remember, you've got to measure this and estimate this, and that has its own complications. But you can see here that amongst condom users, the basic model of a slope of 1 isn't that bad, actually. So for people who are regularly using condoms, it was more sort of random if an infection, quote, slipped through. They didn't use condoms perfectly, or condom fell off, or whatever. But for people who didn't use condoms, the model fit very badly. So that's where other things are going on of the kind I just indicated. Okay. This spawned, actually, these kind of methods spawned a whole bunch of other things, trying to estimate age incidence based on a single cross-sectional prevalence sample is exactly the same statistical problem. Here it is in action in trying to estimate the age incidence of hepatitis A from a single cross-sectional sample. So that's kind of interesting. And this is work that Ruth and I did on what I think of now as the quintessential current status is dying in an avalanche or not. And deaths from avalanches provide current status information because you know the time from the avalanche until the person is rescued. But all you know when you rescue them is are they alive or dead. You don't have good information as to when they died. And this is exactly the same structure. So there's been an enormous amount of work done on that since then. I'm not going to talk about that. I'm going to finish in about 5 minutes with 2 more modern stuff that I've been involved in that are, I think, interesting. And again, good examples of kind of the challenges we're facing now. This was the MIRA trial. I think it stands for Methods to Improve Reproductive Health in Africa. Was a randomized intervention trial funded by the Gates Foundation to look at the effectiveness of diaphragm in protecting women from HIV infection. A lot of science would say, I don't know that that's going to work. Some science, maybe it will, but I'm going to leave that aside. But there was a big trial done of 5,000 women in Zimbabwe and Africa over about 2 years. How do you get a trial like that funded by the Gates Foundation or by any sponsor ethically? Is you have to provide intensive condom counseling and free condoms to everyone in the trial. These were women. And you have to try and make sure it's a really philosophically a dilemma for epidemiologist or statistician. You have to work very hard for ethical reasons to making sure the trial fails. Because ethically you want to see no infection. These are your participants. You desperately don't want to see any of them become HIV positive. But if none of them become HIV positive, the trial is worthless because you'll see exactly the same incidence rates in both arms, 0, and you won't learn anything. So it's another topic to discuss. Here was the results, and these were published in The Lancet. The arms were equal, so I won't bother with the sample size, about 2,500 in each. And there were 150 roughly infections in both arms, almost identical. Unfortunately, slightly more in the diaphragm arm. And when you do a simple comparison, paying no attention to whether the woman used the diaphragm or not in the active arm of the intervention, you get a 5% increase in risk if you use a diaphragm. Not too good, right? In a fairly tight confidence band. So at the lower end, you know, and this is not very plausible estimate, not much indication of any benefit for the diaphragm. And so that was the end of the story as far as The Lancet was concerned. They wouldn't let me publish the next slide. I, of course, cheated and published it somewhere else. But and here was there's another part of the story. Guess what? In the diaphragm arm, there was far less use of condoms. Now, if you were just worried about pregnancy, that makes sense, right? Why? It's overkill. I'm already protecting myself from pregnancy. Why do it twice? So it was not surprising that the women, and I won't get into the details of how these measures of condom use were done, but far less of it in the diaphragm arm. Well, that suddenly, by the way, this was also Nancy Padian's study, that made Nancy think, well, gee, maybe the diaphragm's working pretty well because they're using far less condoms. Their risk must be much higher because of this, and yet they got exactly the same infections. So how do you deal with that statistically? That is really tricky. How you deal with it. How do you account for that to assess that quantitatively? And here's the issue in a very simple causal diagram. Here's the treatment assignment, diaphragm use or not. There's another factor going on here, post-randomization, which is do you use condoms or not? And this was measured at each clinic visit. And the outcome, of course, you're interested in HIV infection. What you measure that I just quoted to you as 1.05 is the entire causal effect of diaphragm use. But part of that causal effect is going down this channel. Being in the diaphragm arm is lowering your use of condoms, and that in turn is raising your risk of HIV infection. What you really want the trial to estimate is this direct effect, not through condoms. We don't really care about that. You might care about it because that might be an issue if in the future in population use of the diaphragm arm, but scientifically you'd really be interested in this. Okay, so that's easy to estimate, right, statistically. We just have to control for condom use. We learned this in graduate school. Got this nasty confounding factor, whatever, I don't know what it's called, something. So I just stratify on it. That's a problem. It doesn't work. It's not a confounder. It's on the causal pathway, on one of the causal pathways. And the trouble is condom use is not controlled by randomization. What controls condom use? Well, lots of things do. How many partners do you have? How old you are? How old the woman was? A whole bunch of things predict whether you might use condoms during the trial. Unfortunately, many of those also are risk factors for HIV infection. So you've got this now happening.
Isn't the same true directly with diaphragms? Even with forgetting.
Well, it would be true, but at the moment, the diaphragm use is up here only. It's intention to treat. Just which arm are you in or not? Let's leave. Life gets much more complicated if you start worrying about did you use the diaphragm or not. That's another issue.
No, I meant it's a confounder. It selects
Well,
on the population just like the.
Let me come to that. I'm going to try and go quickly because I'm expecting 5 minutes, so I want to go quickly. The trouble is when you adjust for condom use by regression or stratification, it induces an association between treatment use and confounders. It's well known. This is what's known as the collider bias problem. And so that when you then look at the relationship between diaphragm use and HIV infection, it is now confounded. So you can't just stratify. You can't just look at the women who use condoms regularly and say, well, what was the effect of diaphragm in that arm? It gives you a distorted result. This addresses a little bit your case. Not only, well, you might think, okay, if I have this causal diagram, okay, I've stratified on condom use to get here. Now all I have to do is stratify on all those confounders. Great, because I learned how to do that in graduate school. I teach that stuff. And slight annoyance is I have to measure all those darn confounders and know about them, but making the world more ideal. Trouble is, what if the use of the diaphragm itself is a predictor of condom use? So in other words, whether I choose to use the diaphragm in a particular sexual contact actually influences whether I choose to use condoms. Okay, it's certainly potentially a predictor of HIV status. That's the whole point of the study. It's a confounder. But I can't put that in the stratification model because that would wipe out this part of the causal effect, which is the very thing I'm trying to measure. So all that great stuff you learn in graduate school of Mantel Heinzel or regression, can't use it. Worthless. So you have to invent new techniques, and gee, time is running out, so I won't tell you how you do it. But you can do it. And by the way, the end of the story was unfortunate in some way. Here is the estimate of the direct effect of condom use, about a 40% reduction in risk. But look at the confidence interval, very wide, so you really can't say anything as a statistician. That width of that confidence interval comes in part because they were quite effective in their condom counseling, and there's not enough people not using condoms to really pin this down, which raises question about the design. So I have a couple minutes left, and I will just go on to the next thing, which is the last thing I'm going to talk about, which brings me right up to now, which is a major trial going on that I'm involved in called the SEARCH trial, which is asking, we know how to prevent HIV. We've known it from the beginning, as soon as we knew it was sexually transmitted, condoms. But what a spectacular failure of public health there has been. We have known this before we knew anything about a potential vaccine. We know how to stop HIV. We can't implement the strategy. We've been absolute abject failures as public health professionals in implementing that in most places in the world. We know the cure to stop it. We can't do anything about it. So now we've got but now we know a whole bunch of other things. We know that circumcision reduces the risk. We know that test and treat reduces the risk. In other words, in clinical trials we've shown that if you give a person who's HIV positive a treatment, that will reduce their infectivity and you reduce incidence. We know that PrEP works. You can take the treatment before you get infected and that works. We all know all of these things in clinical trials. What we don't know is how we roll them out at scale and do them in huge populations, because there's all these unforeseen consequences. So this SEARCH trial is actually looking at the test and treat strategy. If you go into a community and you systematically test people and treat them with HIV who have HIV immediately, do you reduce subsequent infections? That's what the whole trial is. It's going on in Uganda and Kenya. I won't bother in this. Here's the benefits, by the way, of early treatment. Even though you're not sick, you're HIV positive, take an antiretroviral therapy because it will make you keep your health up, but it'll stop transmission to any sexual partners, etc., etc. Here, the two arms of the study are ones testing everyone for HIV in the communities and offering immediate ART, as against in the control arm just using the countrywide guidelines, which are much less stringent. You don't give ART until someone has gotten to a certain CD4 counter viral load. The statistics in here is how do you estimate the causal effect of this strategy? And there's two aspects to that I'm working on. I'm going to run out of time now. So the one strategy is, first of all, to understand that you have to say, how do I estimate incidence in a community? That's not trivial, right? From what we just, at the beginning of the talk, estimating incidence, because people are coming and going. They don't let you test them all the time. And so there's that issue of how you design that part of the study. And once you know the effect in a given community, suppose you really knew a 5-year incidence of HIV, how do you get an estimate of the difference between a treated community and an untreated community? Because their communities are different. There's confounding going on. And that's the second part of the design. I'm not going to talk about it, but the last two slides, if you do look at them, talk about tackling both of those problems separately. And I'm going to finish there. Thank you so much for your attention. I really appreciate it.
Bueno.
Yeah. Yes.
Yeah, my question is that you raised the point of kind of over-adjustment or adjustment for confounding things that is confounding, but because in the pathway of effect, you are inducing bias. So is it possible to happen this phenomenon in the descriptive studies when we may over-adjust for the confounding, or when we control for a variable that we measure, we just control for it and induce bias instead of controlling?
So the question, if I understand it correctly, is that I discussed here adjusting for condoms or adjusting for factors, and that can actually introduce confounding where it wasn't there before. And does that happen in general? And of course the answer is yes. So it becomes crucial that you really understand confounding. Not at the level I was sort of flippantly going through, oh, I understand confounding. The key here is that in this diagram here, let me move back one causal curve. Trying to go back. In this diagram here, as it stands, condoms are not a confounder of the overall causal effect of diaphragm use. And so there's no need to adjust for them if you want the overall effect. And the overall effect was 1.05, the relative risk. The complication that arose in this particular case is that I wanted just this red part, the direct effect, which means I needed to remove this part. The standard way of removing that part, this is a mediator in a causal pathway. The standard way of doing that by stratification is great, but you introduce confounding, and then the story. So this is just as applicable to any epidemiologic study so every time you're adjusting for confounders, you better have a causal diagram in front of you that says, I'm not making things worse.
And the reason for that is the direction of arrow that comes from exposure to confounded. If the direction is reverse, that would be fine anytime, so I wouldn't introduce any confounding.
Right. If I reverse this arrow, it's impossible here, of course, because condom use can't influence the randomization assumption. The statistician gets to choose that, or the dice gets to choose that. But if that arrow were reversed and you had these factors, this would be a classic confounder. And if you adjusted for it, even though there were these other factors sitting out there, wouldn't matter. So the direction of the arrows really matters, that's why I'm saying you really have to understand confounding. Yes?
Did you have a slide with a direct SQ estimate of direct effect? It went so fast.
Sorry, yes. That was deliberate, so you couldn't. I think I had it here and I went through very quickly. This was actually the direct effect of diaphragms amongst women who never use condoms. That's one of the key questions I think that was and should be asked about this trial was, there are certain women who for whatever reason cannot use condoms. They have, one of the attractions about the diaphragm was it's women controlled. The partner doesn't necessarily know that the woman is using this method of protection. Condoms, you can't hide it from the partner, the male partner. And so it's very attractive. And so for women who for whatever reason can't use condoms, it's very important to know, is there any step they can take to protect themselves from infection? So this was a very important group.
That was not in the Lancet, right?
And we saw, sorry?
That was not in the Lancet.
This was not allowed to be published in the Lancet because they said it was not standard statistics. It was a very interesting story because, the trial was published, the whole thing was published in the Lancet. It was an important trial. Immediately got published in the Lancet. Zena Stein and a colleague from Columbia wrote a letter to the Lancet saying, Nick Jewell's an idiot. because obviously condom use is messing up this picture. Then I got to say in the letter back, guess what? We actually had the 2 paragraphs in the paper, but the editors required their removal, and so we got to put it in the Lancet anyway. By the way, and the people who are basically women who were at very high levels of routine condom use, the diaphragm doesn't do anything one way or the other. So these are estimates of the direct effect on the slide. Yeah, this one first, and then I'll come. Yeah.
You mentioned super spreaders, like people who are, for whatever reason, just individually more likely to pass the disease on. Do we know now, like, what the distribution of kind of individual risk of passing things on looks like? Like, is it pretty constant if you're not a quote-unquote super spreader, or is it very individual?
You know, I'm not sure we really know that for HIV still to this day, because you can tell that getting that kind of data is pretty hard. But this concept of super spreader has become key to our understanding of examining any emerging epidemic. There was a lot of interest in that in SARS. It's much easier in a short-term infectious setting because you're getting data over much shorter periods of chronological time. And there it was quite evident that there were super spreaders, that there were certain individuals who, for a number of reasons, were very efficient at transmitting the virus, and other individuals who had lots of contacts, close contacts with SARS, who didn't transmit. And there are, of course, a number of reasons for that. There's probably some inherent biological reasons, but of course it depends on when the contacts occur in the natural history of the disease. So that's become a crucial concept in trying to understand and project the course of an epidemic when you're at the very beginning, as we were with SARS or then with H1N1, is trying to understand exactly the distribution you're asking. I say I don't think we know it yet for HIV, what the distribution of, if you took people, a random set of HIV positive, and said what's their individual per contact infectivity changes, but even if you control for that, I don't think we know. Yes?
Can I just add that I don't think we know either from a medical epidemiologic perspective. The other thing that I don't think we know is the influence of the susceptibility of the uninfected partner. And just these are often couple studies, and so there are 2 people involved, and I think it's been very difficult to sort that out.
Yeah, so the comment there was that there's another aspect that I should have mentioned, so thank you. Another aspect to infectivity, I've been focusing on the infectiousness of the index case, but of course there's also the susceptibility of the other individual, and that also can vary. And of course those are combined together in what I've been calling infectivity. It's the properties of both the index case and the partner that will influence whether transmission occurs. And you're absolutely right, there's fairly strong evidence that certain individuals are more susceptible to HIV infection than others, independently of what's going on in their partner.
Well, I think we've reached the end of our time, but it looks like there are still questions, so we should try to catch them afterwards. And let's thank our speaker again.
Thank you.
I'm Ann Doerr. I just wanted to thank you for your